Want to welcome you to my lecture today. And of course, today we're going to focus on another statistical topic. Statistics is like a story, and a story that goes on and on and on. Today, the focus is going to be on methods of estimation. But you know what? How do we find ourselves in today's topic? Why we need to be doing what we want to do today. I think for better understanding, we need to be able to retrace our step back to where we are now. The whole scenario actually started from estimating the unknown value of parameter. And of course, we want to estimate that using sample information. Of course, we're going to have some methods. We're going to have formula that we call estimator. And of course, since we are going to confront the data set, with the estimator, we actually have a way to investigate whether the estimator is going to do a great job. And that is why we have properties of a good estimator. Of course, in this class, I walk you through unbiasedness property, the efficiency, consistency, and sufficiency. And let me tell you this, the idea of all of that will be in use today. When I talk about sufficiency, of course, we actually use the idea of Fisher-Nehmer factorization theorem, to be able to figure out sufficient statistic. And after figuring out sufficient statistic, we go further to apply Rao-Blackwell theorem to be able to identify minimal unbiased estimator. And of course, by Rao-Blackwell theorem, after you have applied Fisher-Nehmer theorem of factorization, and you're able to get sufficient statistic, of course, the Rao-Blackwell now use that information by trying to look at the function of the sufficient statistic. Looking at the function of sufficient statistic established by Fisher and Nehmer, it was able to show that the expectation of the function of sufficient statistic is equal to theta, which means it's unbiased. And I was able to, acknowledge the fact that the variance associated with estimator given the sufficient statistics is less or equal to the variance of the estimator. So which means by Rao-Blackwell theorem, we're able to derive minimal variance unbiased estimator. Now, if we have done all of that, then why are we interested in this? And I'm going to tell you why we're interested in this. The reason why statistical story continues is because approach, methods are not perfect. Situation where we experience difficulty with applying Rao-Blackwell theorem. What kind of difficulty is that? The Rao-Blackwell theorem use the sufficient statistic derived by Nehmer-Fisher. He used a function of that. He analyzed a function of that. At times, the function of sufficient statistic could be complicated. I'm going to say that again. At times, the function of the sufficient statistic derived by Nehmer-Fisher factorization could be complicated. And the moment it is complicated, it may be difficult for us to derive minimal variance unbiased estimator. I'm going to say that again. The reason why we want to do what we want to do now, which I call the method of estimation, is because of the fact that at times, if I want to go by way of Rao-Blackwell theorem, Rao-Blackwell theorem gave us what? Minimal variance, unbiased estimator, using the idea of the function of a sufficient statistic derived by Fisher-Nehmer. It is not all the time that that function is going to be simple. What of in a situation where that function of sufficient statistic is complicated, then we may not be able to derive the minimum variance unbiased estimator. And if that happens, we're actually going to look beyond that approach and focus on what we want to do today. Now, what we want to do today, we got two methods that we use in a situation where we run into a problem with Rao-Blackwell theorem based on the fact that we may be experiencing a complicated function of a sufficient statistic. And those methods is going to be called one, the traditional method is called the method of moment. Today, I'm actually going to show you how the method of moment works. And another highly sophisticated method that we use mostly, very often in statistical literature is the method of maximum likelihood. The two methods I want to derive today, they are household name method of deriving unbiased estimator. If I want to look beyond Rao-Blackwell theorem, why do I want to look beyond Rao-Blackwell theorem? Because Rao-Blackwell theorem actually rely on the function of sufficient statistic derived via Fisher-Nehmer theorem, which could be complicated. Okay, I want to go into method, method of moment now. Of course, you know why we want to do what we want to do now. I'm going to first start with a motivating example. Of course, everything is going to start from a probability distribution. We got X1, we got Y1, Y2 up to Yn that follow uniform distribution. Of course, uniform distribution has two parameters, right? One is unknown here, and the other one is known. The parameter of the uniform distribution is A and B. A equal to 0 here, B equal to 0. It means A is known, but B is unknown. The upper bound is unknown here. And if the upper bound is unknown, before moving forward, then we need to estimate the parameter that is unknown. Now, we want to make use of a theorem based on what we've done before. If you take a look at this, in this class, we've already showed that the sample mean converges to the population mean. The population mean is the expected value of Y. The population mean is the expected value of Y. The sample mean is Y bar. When you take a sufficiently large sample, if you want to go by what we've done before, okay, the sample mean converges to population mean in probability, okay? And because of that, if you take a look at that, I'm using the method of moment. The idea of the method of moment, since the sample mean converges to the population mean, where do I get theta over 2? Of course, that's going to be the mean of a uniform distribution. You remember, the mean of a uniform distribution is going to be A plus B over 2. A here is 0, B is theta. 0 plus theta over 2. That's going to be theta over 2. And by method of moment, we're actually going to equate the sample mean to population mean. That's how method of moment work. Why do we equate them? We equate them because of the fact that it's at a sufficiently large sample, the sample mean converges in probability to population mean. Then we're going to equate that. When we equate this now, when you solve for theta now, what are you going to tell the world? Estimator for theta is going to be 2Y bar. The estimator here is actually moment estimator. The method of the estimator we derive using the method of moment. This is a traditional way of figuring out our estimator, okay, in a situation where the Rao-Blackwell theorem is complicated, okay? Now, this is going to be consistent. Now, let's now go into a more complicated example, okay? I need you to take a look at this guy now. 1 over S summation Y, that's a sample mean, converges to the first moment. The first moment, the expectation of Y. Second moment, expectation of Y squared. Third moment, expectation of Y raised to power 3. Now, we want to use the fact that a convergence takes place, you know, when the sample size is sufficiently large, okay? Now, that's going to be the first moment. In the first moment, I'm actually going to equate the sample mean, okay, to the population mean, which is going to be the first moment. I'm also going to apply the same to the second moment. Okay, take a look at this. In the second moment, that is the second moment. The second moment is expected value of Y squared. Then, so 1 over n summation Y squared converges to expected value of Y squared. In probability, okay, and don't forget, okay, what the variance, don't forget the variance of Y from statistical theory is actually expected value of Y squared, right, minus expected value of Y all squared. I think you remember that from statistical theory. Okay, from statistical theory, if I want to make this guy the subject of the formula now, it's going to be variance of Y plus the square of the expectation, and that is why you have this guy. The variance of Y is sigma squared, okay, and the square of expected value of Y, that is going to be mean squared, okay. That guy is the same thing as the second moment. So what am I telling the world? What I'm telling the world, okay, if I want to figure out parameter using method of movement, it could be one parameter, it could be more than that. There's a way we're going to do that. Okay, now from the theorem now, based on what we have now, then I can say when you see M, that is the sample moment. Okay, the sample moment, the second sample moment minus the square of first sample moment converges to the population moment, and all of that gives us sigma squared. If you remember Silowski theorem, you're actually going to see if the second sample moment, if the second sample moment converges to the second population moment, and the first sample moment converges to the first population moment, then whatever algebraic operation you perform between them will also converge as well, which means in a way the sample variance converges to population variance. Okay, so that's exactly what we mean. And because of that, we can actually say this guy here that we got by way of the sample is going to be a consistent estimator for sigma squared. Okay, and what is that guy? This guy is this formula here. Okay, that guy, the sample moment, you can see that is a function of the sample, right? So that's a sample moment. We can actually use it to, to represent the population variance. Okay, then I need you to take a look at that. Okay, now let us have a generalization. Okay, if you take a look at this guy, that is a kth moment of a random variable. If k equal to 1, you have the expectation of Y. We call that first moment. If k equal to 2, we call that second moment, which is expected value of Y squared. Now we have a corresponding sample moment. Take a look at this. We got this corresponding sample moment. And if we use the law of large number, Okay, if we use the law of large number, what do I mean by the law of large number? When my sample size is sufficiently large, I expect the K sample moment to converge to population moment. Okay, and the method of movement can be used. When that happens, then the method of movement will now use the idea that, okay, the sample movement equal to population movement to derive the estimator. So the method of movement work, okay, following the convergence of these. Without the convergence of these, there's not going to be method of movement, because the method of movement will tell us to equate sample movement to population movement and find our estimator. Okay, now the next thing we're going to do now, if there exists a function where theta equal to that, when I say theta, okay, that very theta, in it you can have a first movement, population first movement, second movement, until you get a K movement. Then we're going to have another one. There's an estimator, okay, where the first one is going to be sample first movement, sample second movement. Then it has been proved, statistically and mathematically observed that our theta cap is actually going to be a consistent estimator. Of course, you know what I mean by consistent estimator is that when n tends to infinity, the variance of the estimator converges to zero. Okay, so the way the method of movement work is what I have just explained right now. Before I go into the method of maximum likelihood, let me first see whether I provided example here on the method of moment. Give me 1 second. Okay, this is what I'm going to do now. Of course, that is the example that I've provided here. The first example here. In the motivating example, I'm going to here. The idea behind method of moment, when you know the mean of the distribution, equate the sample mean to that mean. So y bar equal to theta over 2. What is my theta? Solve the equation. The theta is going to be 2y bar. So the theta equal to 2y bar here, it means that is the method of moment estimator. Does that make sense? That is the method of moment estimator. You can be given any distribution. Okay. What will be the method of moment for normal if mean is unknown? Then I'm just going to equate the sample mean to population mean. For normal, it's just going to be our theta cap. Our theta cap is equal y bar. I'm done. For normal, for mean. Okay. Our theta cap equal to y bar, which means what have I done? I equated the sample mean to the population mean. Okay. For normal, it's very, very simple. I can give you any other distribution. Like, okay, my TA this week, I was going to walk you through some problem. You can be given maybe exponential distribution, and they want you to use the method of moment. Okay. Now, that is how the method of moment works. It's very, very easy. But you know what? The method of moment is not the best. You know why? Because the method of moment is not based on sufficient statistic. I'm going to say that again. That's why it's a traditional method. It's not based on sufficient statistics. Any method in statistics that is not based on sufficient statistics is not going to work all the time. Okay, because of that, we're going to go into another method that is highly sophisticated that we call the method of likelihood. The method of likelihood actually use the idea or is based on sufficient statistic in a way. Now, let me, when I say method of maximum likelihood, what do we mean by likelihood? Okay, I said in practice, it is often possible to specify the PDL of EM of a random variable up to some unknown parameters. Okay, you want to specify your distribution. You're actually going to have unknown parameters that we need to figure out. Okay, whether you're working with PMF or you're working with PDF. Now, if I have Y1 up to YN IID, the likelihood function is the same as the joint PDF for continuous, joint PMF for discrete. What do I mean by that? Okay, what I mean by that is, mathematically speaking, if you take a look at this, the joint PDF or joint PMF is to multiply the distribution, okay, across the sample size. And why are we multiplying them? Because of the fact that we said they are independent. Variables are independent. You remember in statistics, in particularly in a probability class, what is it? With A and B are events and they are independent, the probability of the joint occurrence will be equal to what? The product of the marginal probability. Okay, so that's why you see here, you can see product. Because if you want to use the method of maximum likelihood, you need to first understand the likelihood of a distribution. Oh my God. If you remember Fisher-Nehmer theorem of figuring out sufficiency, they also make use of the likelihood. But in the method of movement, we didn't make use of the likelihood. Okay, and that was why the method of movement was not based on sufficient statistic. But here, we want to make use of the likelihood. Okay, now so when we have the likelihood now, what we actually want to find, okay, let's say I've defined the likelihood is just going to be the joint, okay, which is going to be the product. And what you're trying to say now here, you are talking about the joint. What is the probability? The first person I interview is going to be Y1. The second value is going to be Y2 and so on, giving the information. That is the joint. So I'm giving you here for discrete and continuous. And of course, L is for likelihood. So the likelihood is that. So if the likelihood is that, okay, what I'm doing now, I'm defining the likelihood. Now I want to go into distribution now. How do we get the likelihood? For instance, if I'm working with the Bernoulli distribution, if you take a look at this guy, what does that mean here? It means I want to take a 10. I want to observe just 10 people. Maybe here I want to ask them whether they approve the job the president is doing. I expect them to tell me yes or no. Don't forget, we label yes as 1, label no as 0. And what we want to figure out is the parameter theta. And the theta is the proportion that lies between 0 and 1, right? Okay, now, and here, and n equal to 10, n equal to 10, okay, because n equal to 10, then I'm actually going to be talking about binomial, okay, don't forget, and there are 2 possible outcomes, okay, and I want to figure out theta. If I want to find the likelihood of that now, this is the formula, then I need to find the likelihood of binomial distribution, okay, and my I is going to start from 1 to n, but in this case, my n is going to be 10. We're going to choose a sample size 10. Now you can see that's a binomial probability function, okay. Now the likelihood of that is just to write the product. Like we want to have that n times, that is 10 times. Now if I want to write that now, okay, when you take a look at this now, the product of this, if I have theta raised to power y, if I have that in n time, it's going to be this, right? Then what about this? This is going to be in n times, it's going to be 10n minus summation y. This is the likelihood now of the binomial distribution. Okay, now when this is a likelihood of binomial distribution now, okay, now what I'm doing now, I'm just getting the likelihood. It is after I've derived the likelihood function of a distribution that I can now use the method of maximum likelihood. The very first thing we do is just to first derive the likelihood of any given distribution. Okay, I also want to walk you through how to derive the likelihood of a normal. I'm going to get to normal. After that, showing you some example on how we derive likelihood function. Then I will now walk you through how to maximize the likelihood. Maximizing the likelihood is just to apply the principle of optimization in mathematics. But I'm still coming there. Okay, I'm still coming there. Let's go to number 2 now. Okay, y1 up to yn follow normal distribution. Here, there are 2 parameters, okay, and the 2 of them are unknown, which means we need a maximum likelihood estimator for mu. We need a maximum likelihood estimator for sigma squared. Okay, now how do we write the likelihood now? I'm gonna go into the okay, now writing the likelihood now. If you take a look at this, given what? Given 2 parameters, mu sigma square. Here, there are 2 parameters. So I need to first write the probability distribution for normal. Then I'm going to put the product. Putting the product now, then I want to get the likelihood. Now, if I want to apply the product now, don't forget the product affects all of them. If I want to apply the product on this guy now, mathematically speaking, it's going to be this. In n time. That's a constant, right? It's going to be in n time. And if I want to apply that here, because that is on the exponential, it's on the exponent, then there's going to be summation y. There's going to be summation y. You see the summation? There's going to be summation. Okay. Now, anywhere in the world now, this is the likelihood of a normal distribution. This is the likelihood of a normal distribution. Now I'm still coming back, okay, to maximize the likelihood using the principle of optimization that we're going to borrow from mathematics. In any statistical study, particularly in the theory of statistics, mathematics is the key. Does that make sense? Okay, now we want to go into a motivating example now for MLE. MLE means maximum likelihood estimation. Now we got 3 balls, red or white, in a balls. What is the goal? Estimate the numbers of red balls. How many red balls? We got 3 balls distinguished by red or white, and we want to estimate the numbers of red balls. But you know what? We know possibility. If I got 3 balls, if the random variable represents the numbers of red balls, then the parameter space is going to be 0, 1, 2, or 3. It's either none of the balls is red, or 1 is red, or 2 is red, or 3 is red. That is possibility. Okay, now we need to perform experiment now. Okay, now the experiment, draw 2 balls without replacement, and let yi be the color. Of course, you know what we've done before. We're actually going to have a label, right? We're focusing on red. Why? Yi is going to be 1 if the ith ball is red, and it's going to be 0 otherwise. Okay? Now, if you take a look at the outcome here, this is a possibility in the outcome. Okay, the first ball may be red, and the second may still be red. Does that make sense? That's why I say 1, 1. Okay, now when you take a look at the solution now, we're going to consider possibility of, we want to choose 2, right? 2 balls. If we want to choose 2 balls, there's possibility of this. What does it mean? 0, 0. The first time I choose no red. Second time, no red. First time, no red. Second time, red. First time, red. Second time, no red. Then this guy is the one here. Is that not a possibility? That's possibility, but we choose 2 balls. Now, and don't forget the state of nature that we considered the other time in the theta. We're going to consider that now. When theta equal to 0, okay, what you see now, when theta equal to 0, what does that mean? No ball, no red balls. No red ball, of course, we correspond to 0, 0, right? Which the probability, the joint probability is going to be 1. So these are possibility. You see that? That's a possibility. Okay. Now, if I want to talk about the likelihood now, okay, I need you to come to this guy. Okay. Now, likelihood in terms of probability, check the table. You're going to see 0, 1 over 3 and 1, right? Is 0, 1 over 3 and 1. Is 0 occur where? Where does the 0 occur? If you take a look at this guy now, okay, that actually 0 occur at 0, 1, at theta equal to 0, theta equal to 1. Then for theta equal to 2, you have 1 over 3. And for theta equal to 1, we have theta over 3. Take a look at that. But you know what? A reasonable choice would be to choose the model with the highest likelihood. That's why we call it maximum likelihood. We want to choose the highest likelihood, which is like, what is the highest likelihood, for the observed model, which is theta equal to 3, at the highest likelihood, like the highest values of theta. But you know what? If we want to do that, we want to go into the approach now. After getting our likelihood function, we are seeking the expression for theta, okay, where that will be, where the likelihood will be maximized. And the theta that we're going to get at the end of the day is going to be called maximum likelihood estimator. Maximum likelihood estimator. How is it going to work? I'm going to show you now. Let's get started. Okay, go ahead. Where? Yeah. Actually, here we are not. This is not a good way to choose. Because at times, when you take, okay, for instance, for theta equal to 3 now, okay, if you take a look at possibility 0, 0, 0, 1, that's what I mean. So what we can do is we can go by way of optimization, because this could be deceiving. Okay, so if we go by way of optimization, if we obtain a likelihood function, then we just try to maximize that by taking a differentiation, performing derivative with respect to the parameter. Then after which, what are we going to do? We're going to set it to 0. Then we're going to solve for theta. They use that method in optimization in mathematics. And because of that, is because this may be deceiving. And that is the reason why we want to come here. We want to be able to, if you take a look at this now, take a look at this example. A binomial experiment consisting of n trial resulted in observation that find the MLE of P. We don't want to go by table. We want to go by using the idea in mathematics. The very first thing, like I said, for Bernoulli, this is the distribution for Bernoulli, right? Then what is this guy doing? I want to get the likelihood. Now, finally, this is the likelihood. Now, after getting the likelihood, you know what I'm going to do? The very first thing is to go by differentiation. But before we do differentiation, we first of all take the logarithm of the likelihood. What did I say? You can see all this as a power, right? When you take the log, it's going to break it down, going to be the power down, right? Now, and that was why I said, notice that log is a monotonically increasing function. So hence, maximizing LP is equivalent to maximizing log of it. So what we're going to do now, okay, we're going to take the log of the likelihood. Taking the log of the likelihood, you see what we have, mathematically speaking. You see where we are? Now, After when you get here now, you now perform the derivative with respect to the parameter. What was the parameter? P, right? We're going to differentiate this guy now with respect to P. When we differentiate with respect to P, we got a sufficient condition. Right now, we're back in mathematics where we do optimization. If you really want to know whether you maximize what happened, the second derivative must be less than 0. Do you remember in mathematics? Okay, that was why we actually have a condition. We do the first derivative, we do the second derivative. Before we move ahead, the second derivative must be less than 0 for maximization. And of course, when we do the first derivative, now take a look at this. What have we done here? We've done the first derivative with respect to P. After doing the first derivative, you equate it to 0. You equate the resulting expression to 0, then you solve for P. When you solve for P, what happened? That is all you got. P cap MLE. Why am I putting MLE? I'm trying to say, oh, this is an MLE estimator. That equal to Y over N. If you check, that is the same thing we got for the minimum unbiased estimator through sufficiency. You remember for P cap gave us a Y bar. The sufficient statistic by Fisher-Nehmer was summation Y. Do you remember? And if the summation Y, the function of the summation Y was summation Y over N, which is Y bar. And Y bar is a minimum variance unbiased estimator. Now, you can see what happened here. The maximum likelihood estimator is the same as the minimum variance unbiased estimator here. And how do I know whether this is going to do the job? When I do the second derivative, they all gave me negative. Look at that, negative, negative. If you really want to know whether that will maximize, then what you need to do is to perform the second derivative. That should be negative expression. So therefore, here, that is the maximum likelihood estimator. Okay. Now I'm going to go into another example. Take a look at this guy. This time around, I'm actually, by the time we did sufficiency the other time, using Nehmer, using Fisher-Nehmer factorization theorem, the sufficient statistic we got for this under Nehmer was summation Y and summation Y squared, right? And the minimum unbiased estimator when we actually apply Blackwell theorem for mu was Y bar, sample mean. For sigma squared was S squared, sample variance. Now, let us now investigate here. Let us obtain the maximum likelihood estimator of this. The very first thing we're going to do, because we're dealing with the normal distribution, we need to get the likelihood function. After getting the likelihood function, what is the next step? Take the log of the likelihood. Don't forget, write it down. Take the log of the likelihood. When I take the log of the likelihood, this is what I have. But let me tell you this, because there are two unknown parameters, mu and sigma squared, I'll first differentiate with respect to mu. I'll set to 0 and I'll solve for mu. Then I will also differentiate the function with respect to the variance. Okay, and set to 0, and I'm going to solve for that. Okay, that's what you see me doing here. And after that, and let me tell you this, when you are differentiating with respect to mu, the other parameter will be regarded as a constant. Okay, that is why you see a partial derivative. You can see a partial derivative. Okay, now when you equate after differentiating with respect to mu, you set the expression to 0 and you solve for mu, it's going to give you Y bar. After differentiating with respect to sigma square and you set to 0, it's going to give you this guy. Now, what is going to be the conclusion now? The MLE, the maximum likelihood estimator for mu, is going to be Y bar. For the sigma squared, it's going to be that guy. That's what we mean. Now, and if I know the maximum likelihood estimator for sigma squared, of course, I will be able to know the maximum likelihood estimator for sigma. The square root of variance is sigma. Then I can just say square root of that. I'm done. Any question? What you need to do, you need to revise your knowledge of calculus and algebra. Number one, if you want to get the maximum likelihood estimator, you need to first get the likelihood function of the distribution. After getting the likelihood function, you take the logarithm of the likelihood. After taking the logarithm of the likelihood, then you differentiate. You perform derivative of the log of the likelihood with respect to the parameter. Then you set it to 0. Then you solve for theta. That's exactly what we're doing here. Okay. Now I'm going to go to what I call invariance property of MLE. If theta cap is an MLE of theta, then a function of theta cap is also going to be an MLE of T of theta. That's an invariant property. Now, let's take a look at this. Example 9.16. Okay. Let y1, y2 up to yn be a random sample of observation from a uniform distribution with probability density function 1 over theta, and where y1 lie between 0 and theta. Find the MLE of theta. Now, I'm going to tell you this. One of the way to show that method of maximum likelihood is better than method of moment is when you are seeking to estimate parameter from a uniform distribution. Okay. Now, if I want to use the method of moment, what do we get the other time for this? When we started, the method of moment is just going to equate theta over 2. Don't forget, do you see the range? 0 and theta, right? A is 0. Now equal to what? Equal to y bar, right? Equal to y bar, right? What does that imply? For method of moment, what does that imply? For method of moment, it implies your theta cap is going to be what? 2y bar. Your theta cap is going to be 2y bar. But if you want to go by method of maximum likelihood, we need to first get the likelihood function of a uniform distribution. You know that's going to be a likelihood function, right? And let me tell you this. We may not be able to, when you take the log of this and you try to differentiate and that, you may not be able to optimize the uniform. You can try now because we're looking for theta, which is the upper bound. Okay. We're looking for theta, which is the upper bound. Okay. Then that is actually going to be a decreasing function, which means we need the minimum. The minimum of theta is what we're going to be seeking for. And because of that, we're going to consider the maximum order statistics. Now, when you take a look at the MLE, okay, because that function, the likelihood function for uniform, is going to be monotonically decreasing on that, monotonically decreasing. So it's going to be maximum. And let me tell you in the end, you can write this guy down for MLE for uniform. If you want to have a special one, it's going to be n plus 1. It's going to be n plus 1 divided by n. Okay, y, the maximum order statistic. Okay, now take a look at it. This is MLE. I want to give you an extra credit problem that you can send to me. Now, this is the MLE, okay, for uniform n plus 1 over n, the maximum order statistics. Okay, what is the method of movement? I think we got to Y bar, right? We got to Y bar, right? Now let me tell you this. We can actually ask you to investigate. Okay, now you know what I'm giving you to do here. Okay, I want you to investigate which of the two estimator is better. What are you going to investigate for? I need you to investigate efficiency and consistency. If you want to investigate efficiency, you want to look at the minimum variance, right? Right? And if you want to investigate consistency, okay, as n tends to infinity, you want to see whether the variance is going to converge to zero. Now, who can tell me? Okay, I'm not. If you want to compare the two, you need to get the variance of 2y bar. It's going to be 2 squared variance of y bar. Where is it going to come from? You know the variance of y from this uniform, right? By using b minus a all square over 12, which is theta square over 12. Then from there, you'll be able to know the variance of y bar. It's going to be in terms of n. What about this guy? Oh, before you can get the variance of all, n plus 1 over n yn, it's going to be n plus 1 over n all square variance of yn. Then you need to first use the formula of maximum order statistics to get the expected value of y, to get the variance of y before you're going to plug in here. Now, I'm giving you this as something you can add to your grade for those of you who are interested. But let me tell you this. When you are done, that of the variance of the MLE is going to be smaller than the variance of the moment estimator, because the two of them, they're going to be in terms of n. And at a sufficiently large sample, you're actually going to see the variance of MLE will be smaller. And because of that, we're actually going to conclude that asymptotically, okay, the maximum likelihood estimator will be more efficient than moment estimator. And the reason why it is more efficient is because the likelihood function was based on sufficient statistics. Because when we're using the idea of Fisher-Neyman to derive sufficient statistic, Fisher-Neyman put into consideration the likelihood function of the distribution. It was able to factorize that into two functions. And here too, in the method of maximum likelihood, we make use of the likelihood function. Now I'm giving you this as an assignment. I need you to derive the variance of the two estimator, compare them. When the sample size is large, but I'm trying to tell you now, that of the MLE will be smaller. And that's why MLE is preferred. And the question before I go. Now, before I go today, I've already upgraded the midterm 1 for those who actually did a makeup. When your grade did not change, then it means maybe somebody performed poorly in the makeup compared to the original score. So the original score will stay the same. But if your grade change, it means then you perform better in the makeup. Okay, make sure you stay safe and see you on Wednesday. Bye for now, everyone.